Welcome back, Algebras. I'll have you know that I only died once in the nether and had to respawn like 50 times to go get all my stuff because I spawned right in the middle of a mob. Awful. All right, today we are going to start looking at Chapter 2. And I've mentioned it over and over. The nice thing is that after we've done this really big kind of broad review of a bunch of the different things that we saw in Algebra 1, we are going to be still reviewing, I think, but we are much more focused, and I'm just going to assume, like, no offense, but that nobody remembers any of this stuff. Because I don't want to make assumptions, because if somebody doesn't really remember it, that's not going to be helpful. So, Chapter 2, our entire focus throughout the next several sections will be on quadratic functions and equations. All right, I think this is, I'm trying to remember how many sections there are. Not a huge deal right now. Okay, for today specifically, we are going to start 2.1. And I guarantee we won't get through it all today. But really, our main focus, it's going to ring a bell with stuff that we've seen. And if it didn't click when we did it in Chapter 1, that's okay, because we're going to make it click here. So our focus today is looking at how does one go about transforming quadratics. So obviously we're going to be talking about quadratics. It's like our focus that we're dealing with. My biggest concern is making sure that we can all agree on what exactly a quadratic is. So our main bullet point is going to be focusing, and it's going to be a definition. We're going to be talking in depth about what it means to be a quadratic function. Okay, I think that you guys have likely seen and heard the word quadratic for like, I would say 3 months of your Algebra 1 course, if not more. Anybody remember what a quadratic is? What, if I said just write any quadratic function on your page, how many of you think you could do it? Okay, Amy, what would you write? X squared. Anything that has x squared, and that's the biggest power of x, we're good. We have a quadratic. Now, we're going to define that a little bit nicer because there are some weird situations. The easy way that we're going to define this in here without being too crazy formal is a function, which normally we'll use f of x, but a function that can be written as, and I'm going to let you guys catch up because all we need is this very first little piece. A function, any function that can be written as, we'll call it f of x, and it always has this general form, ax squared plus bx plus c, where the only requirement is if I let a be 0, does it have an x squared anymore? And it wouldn't be quadratic, right? It would just be a linear function. We don't look and see mx plus b, but it's the same format. Only thing that we need to say is where a is not equal to 0. That's it. If you can write your expression, your equation in this form, you have a quadratic. Now, there are some other nice things that we can say that make it really wordy. We're not allowed to have anything but a 2x squared, x to the first, and a constant. We can't have imaginary numbers. I don't think you guys know of imaginary numbers yet, but it's coming. There's no x in the denominator, just these. Okay. As we deal with this, we're going to look at how does one go about graphing these. Now, within quadratic functions, there are several different ways that you can graph them depending on the form that it's in and the way it's presented. We're going to start today with real easy form. So, Amy pointed out just a moment ago the most simple quadratic function that exists. What's the easiest possible value that we could have for a and b and c? 1 for a. What's the easiest for b? I think if 0 would be easier, wouldn't it? Because if it was just x squared plus nothing else, that's as simple as that gets for something of that form, x squared. So we're just going to make a quick little note. the parent function. Which, somebody remind me, what's the parent function? Like, what does that mean? The original, the most simple, that hasn't been moved anywhere. The parent function of the quadratics is y equals x squared. Now, we could say y, we could use whatever it is. That's it. What is the shape of this? Say that again? It's not quite a U, and you're close. My issue with U is that if you draw a letter U, do you guys agree that these wind up going straight up? Okay, quadratics don't really do that. Quadratics go out like this, and they might get really steep, but they never go straight up. Never. Okay, so when we're looking at this, we're just going to define it, and we'll graph one here in a minute. It's a parabola. And if you need it, we can do this, and I'll make it really try not to go all the way straight up, but it looks like this. Satellite dishes or satellite telescopes that we might use to look out into the cosmos, we use this shape because there's something really nice that happens when stuff reflects off the sides of a parabola. Okay, if we wanted to graph one like we did on the bell ringer, we see that it's kind of gross to do, right? So we're just going to go ahead and make one last comment. Graphing something that looks like ax squared plus bx plus c, in all reality, it can suck. This can be gross. Here is the really good news about it. Because it's gross, mathematicians, and not just because it's gross, but it's just something that works out, there's a different way that we can write these that makes it link up with some of the things that we saw in section or chapter 1, but also makes it crazy easy. So here we are, graphing. I don't want to talk about graphing in this form yet. That's what the bell ringer was. We'll get to it. But let's talk about a very specific form. We are going to define, real quickly, what is known as vertex form. Now, you guys, I think, have seen the word vertex. What's the vertex of a parabola? Like if I have a parabola here, or with my hands, where would you say the vertex is? The center. So right up in here in the middle of it? So let me do it here so you can see it. Is this the vertex? No. Not quite. Just move it down. So like all the way down here. Okay, it's like what would be the pointy part if it weren't rounded? Okay, the very minimum value if it opens up. What if it opens downward like this? We now have a maximum, and it's always at the vertex, up at the top. Okay, for our vertex form, we're only going to define it with how it looks. F of x equals a times x minus h squared plus k. Where have we seen anything that looks like this? Last chapter, when we talked about transformation stuff, right? So, just real quickly, we've already defined all this, but I want to make sure that if you didn't notice this is something we've talked about significantly, I want to hit it really quickly. What does this value change? A. So, reflection and stretching or compressing in the vertical axis. So, we'll say a couple statements just as a reminder. Totally up to you if you want to have this. This can deal with stretch and compress. And we're going to write down a couple little things there. When we talk about stretching and compressing, it stretches, which makes it thinner. If whatever that value of A is, if its absolute value is bigger than 1. That means that we have a stretch, we've gotten thinner. And I'm going to just make sure that that's there. What if I want a compression? Something a little wider. So the absolute value of A should be less than 1. Now, the only reason that I'm really hitting this absolute value part here, and it can be kind of ugly to think about, is exactly what Amy mentioned a moment ago. If A is a negative number, I can imagine a parabola that's down but it's thinner. What changes whether it opens up or down? The negative. So we're just going to go stretch and compress, and then additionally, and reflect. Over which axis? Good. Over x-axis. If, notice it's just A, not the absolute value, just A itself. So if I have negative 12 in front of my function, I know that it's 12, so that number has been way thinner, but it's also been reflected. Okay. What about this value of h? So good. I'm going to say horizontal. And instead of just saying left and right, I'm going to actually call it by its real name, a horizontal translation. Okay. If h is positive, like a 5, we would have x minus 5 in here. It would move right 5. I'm not going to rewrite all these rules. We have them. But positive to the right 5, negative to the left 5, and it switches signs inside because of x minus h. What about the k? Vertical translation. Love it. So we'll go, let's see, translations feel blue to me. Don't like that. We'll just go here. Vertical translation. If I have k is plus 5, which way did my graph move? Up 5. What if it was negative 2? Down 2. Okay. Everybody see very clearly that this is the same thing that we were looking at before, but we're going to be much more focused. What didn't I include? The value of b. And we didn't do it because whatever b is, notice this thing has a 1x on it. We have done away with it. Okay. As we're looking at these, the last important thing, and all this is just review, but I want, this is still continuation, sorry. In this form, right off the bat, does this look nicer or uglier than what we did on the bell ringer? It looks nicer to you guys? I would agree with that, but here's the big, really handy part. H comma k, these numbers that are also in here, this h comma k is the vertex. Every single time. This form, which is called vertex form, is called so because we have our vertex written in it. Additionally, if you happen to move tomorrow, hope not, but it could happen, you may see this form of a quadratic called graphing form instead, or standard sometimes. But we're going to call it vertex in here. Okay. Should we graph one? Let's do it. And we'll probably have time to graph one together and one on your own, and then tomorrow we'll be getting some word problems. So let's dive in. Example, I want us to graph, so make table, make a table, and find, and I have several things that I want us to find here. We're talking about all of our key features. Now, depending on who you ask, we could have a bunch of them, but I want us to explicitly state, after we've done our table, where is the vertex, the axis of symmetry, which you will never see me write this again. Any suggestion or guess on what my shorthand for axis of symmetry might be? AOS. AOS. I also want to find my extrema, which I doubt you guys have ever seen that word. What does it kind of look like? And if I talk about the extreme of a parabola, what do you think I'm referring to? The highest point or the lowest? The min or the max? Either one. Okay, that's what I'm after. Additionally, we'll just add it because they're always going to be included. The domain and the range. Okay. When you are graphing quadratics, I want you guys to use tables at least to begin with. After a few days of doing it in this form, you'll maybe be able to get a good picture in your head. Your calculators can also do them, but I don't care if your calculator can do them. I think that legitimately we can probably graph these faster by hand as long as we have a nice approach. Then you can type it in and graph with your calculator. Question or just stretching? Okay, cool. So let's do our first one together. I want us to graph the function f of x is equal to, I don't know, let's do negative 3 x minus 1 squared plus 4. Okay. While we go through this problem, we could do a ton of annotating, but I think that if we just work the problem and make little notes as we go, as long as you're paying attention, we'll be all right. Okay, right off the bat, without anything else, can you guys tell me where the vertex is? So I have two suggestions, either 1, 4 or negative 1, 4. What do you guys think? It's 1 because x minus h, and I'm just said h is 1 in this case. So right off the bat, I'm going to start there. Vertex It happens to be at the point 1, comma 4. That's h and k in my graph. Before we make our table, can you guys tell me what sort of changes have happened? Has this thing moved left or right? It's moved right how many units? 1. Did it get thinner or wider? Thinner. How do you know that? This absolute value is a positive 3. It's 3 times thinner. What's the negative here going to do? So instead of opening up and having a minimum, it goes down and has a maximum value instead. And then lastly, what's this do? It goes up 4. Realistically, you might be able to get a really good sketch just with that information. It got thinner, it moved right, and it moved up. And it reflected. Okay. However, I want us to make sure that if you can't do these things in your head super quickly, and that's completely fine, we have a nice systematic approach to make a table. I'm going to take this vertex, and when we make our table, my vertex x value, which is 1, it goes right in the middle. Right in the middle of our table. So let's do that. Negative, I'm going to have an x. I'm going to show my scratch work inside. We have a negative 3, x minus 1 squared plus 4. And would you rather I write y or f of x over here? Why? Does it really matter which one I write? Not particularly. Okay, so I'm going to make enough room, and we're going to put the x value of the vertex where on this table? Right in the middle. And what I mean by that is not like right here, but let's do it right here, a 1. Now, I don't know if you guys have picked up on this yet, but I'm kind of a nerd, and I kind of like math. Back in my day when I went to college, I was fortunate enough to live with like one of my very best friends from where I grew up. So when we wanted to go back to our hometown, we would drive together and we'd go for a ride. Now, I went to the University of Wyoming, and I don't know if you guys have ever been through Wyoming. Anybody ever driven through Wyoming? What do you think there is between where my university is and my hometown? Mountains, there's certainly some, and then yours was also good. Nothing. Okay, which means we didn't have phones like that would work throughout the whole trip because it's out in the middle of rural America. You guys ever play like license plate games while you're driving? Yeah. But here's the deal, you can't if there's not really any cars there because again, you're in the middle of rural America. So we used to play a game that we would call squares. And then we'd play cubes afterward. You guys want to try a round of squares real quick? You guys know your square numbers. No. Do you know how to square a number? Yes. Like if I said, let's find 1 squared, how do you do it? 1 times 1. Okay, we all know that 1 squared is 1. So check it out. There's only 23 of us. I'm going to start. 1 squared is 1. He will now square what numbers next? 2. What's the square of 2? Square the next number. 3. So 3 squared is? 6. And I'm sorry, you should have said 4. 2 squared is 4. 3 squared is 9. 4 squared is 5? 6? 7? We're going to pick up right here. We're going to do a round of squares tomorrow. I'm going to go randomly so that you can't, like, preface it. Cool. We're going to use that to our advantage here. At the start of class, I'm going to pause right here. There is no homework. At the start of class, we will put the bell ringer tomorrow in our notes. We're just going to finish this problem for our bell ringer.